Hey, welcome back, guys. This is the second assignment on logistic regression. So, in today's assignment, we will see variable selection techniques and apply it on a classification problem. We have already seen three methods earlier in linear regression. Now, in this assignment, we will do ridge regression and lasso regression. So, we will start by reading the overview of the problem as shown here on the screen. And we'll try to predict whether or not an individual suffers from diabetes. The complete dataset description can be found on UCI website or Kaggle website or GitHub website. The data consists of 767 individuals, 8 features and 1 nominal class variable, that is 0, 1, where 0 and 1 denotes the absence and presence of diabetes respectively. Now let's start with the question 1. Question 1 says, read the data and prepare data for analysis. So we will read it using the read.csv function and then store it in the variable diab. Then we will check the structure of the data using the str function. It says 767 observations are there of 9 variables. On the left hand side you have the variables. Then their type is printed on the next column. And then few values are shown for each of the variable. Then we'll proceed to split the data into training and test part. So first we will set the seed. And then we will use the sample function. Now the first argument here is a vector of 3 true and 1 false. So sample will be drawn from this vector. Then the size of the sample is equal to the number of rows of the data set. And then third argument is replace is equal to true. So we will run this and we will store the value in a variable called train. Then we will create another variable that is test. Now this variable will have all the values other than the train. If a particular observation in the train is true, then the test variable will store it as false. And if a particular observation in train is false, then test will store it as true. So this is how we have created two variables that we will use for creating the train and test split. Now next step is to separate the predictor and response variable. So for this we will create a matrix using model.matrix function. Now the first argument for model.matrix is x1, which is the dependent variable. Then we will mention the data, which is the training data. So we will use train variable to subset our data frame, which is stored in diab variable. Then we will close the bracket and further subset the column 1. Now we are subsetting column 1 because model.matrix function creates an intercept column automatically. This intercept column is column 1. And as we are creating predictor matrix, so we don't need intercept column. Therefore, we are dropping it by subsetting it. So we will run this entire code and we will store it in the variable x. So this variable x is our predictor matrix. Now we will create another variable y. This will contain the first column of our data frame. So we will use our data frame diab, then subset it using the train variable, and then further subset it to extract the column 1. Also, as column 1 is the categorical variable, so we will convert it into the factor using the s.factor function. So this way we have separated the predictor and response variables. Now why we have separated the predictor and response variable, the explanation is given below. Now the first point here says we will be using glmnet function for performing ridge regression. And this function does not use our usual y tilde x syntax that we have been using in all the regression functions. Hence we have used model.matrix function to create a matrix of predictors. This also automatically transforms any qualitative variables into dummy variables, and it is required for our analysis as GLMNet only accepts quantitative variables. Also, as I said earlier, from X we have excluded column 1 because when you create matrix using model.matrix, it creates a column of intercept with values is equal to 1, which is not required for our analysis. Now let's move on to question 2. Question 2 says, perform ridge regression and make the prediction. So for this, first we will load the library glmnet. Since it is an inbuilt feature, we don't have to install any packages. We will directly load the library using the library function. Now once the library is loaded, we will perform ridge regression using the glmnet function as shown here. Now here the first argument is our predictor variable. The second argument is our response variable. So that was the reason we have separated predictor and response variable in the previous step. After that, the third argument is alpha is equal to 0. And then family is equal to binomial. Now let's see the explanation of this code. Now the first point says alpha is equal to 0, which is the default, is used for ridge regression, and alpha is equal to 1 is used for lasso regression. Then the second point says glmnet function performs ridge regression for an automatically selected range of lambda values. However, we can also specify the range of lambda, but in the above code we have not done it, so glmnet function automatically selects the range of lambda values. The fourth point says by default the glmnet function standardizes the variables so that they are on the same scale. To turn off this default setting, you can use the argument standardize is equal to false. And the fifth point says in case we want to vary the lambda values, then we can vary in this range. So we run the above code and we store it in a variable diab_ridge. So that is how we perform ridge regression. Now next we have performed ridge regression again. In this case everything remains the same except that we have varied lambda manually. Now for lambda we are using 10 raised to the power SEQ. SEQ is a function that will generate sequence. It will generate a sequence between 10 to -2 with a length is equal to 10. So that is how we define the value of lambda manually. Again the explanation is given here. You can read through it if you have any doubts. Now in the next part we will predict the test data using the ridge regression model. Now for predicting as well, we will have to separate the response and predictor variable. So we will create a predictor matrix from the test data using model.matrix function as we did above. And then we will create a vector y_test which will store the response variable from the test data. Now after separating the predictor and response variable from the test data, we will make the prediction. The first argument for predict function would be our model, which is stored in diab_ridge. Then the second argument would be the predictor data, which is stored in x_test. And the third argument type is equal to class. We will run this and we will store the results in a variable diab_pred_test. Now in the next part, we will see the test error using the confusion matrix. So we will use the table function. The first argument is the response variable of the test data, which is stored in y_test. And the second argument is the predicted values, which are stored in the prediction results in the variable diab_pred_test. We are also subsetting the first column using the square brackets because the prediction results are stored in the first column. We will run this and we will store it in a variable cf_table. And then we will print confusion matrix as shown here. Now we can sum the diagonal elements and divide it by total values. and then subtract it from 1, this will be our misclassification error. So it is coming out to be 27%. Now let's go to the next question. Question 3 says use cv.glmnet function to build the model and make the prediction. So we could also use cv.glmnet function to find the model with the best lambda instead of putting lambda manually, and then use the value of lambda in predict to make the prediction. So first we will set the seed here. Then we will use cv.glmnet function. First argument is the predictor, which is stored in x. Then the second argument is the response. Then type.measure is the third argument, which is class. We will see what type.measure is. But before that, let's put the other arguments. N-fold is equal to 10. And then family will be equal to binomial. So basically cv.glmnet is a function that uses cross-validation. So what cross-validation does is that it divides the data into random folds. Here number of folds is equal to 10. So it will divide the data into 10 random folds and then create the model and calculate the error and value of lambda for each of the folds. After that, we can select the best lambda using the minimum error. So this is how we improve the efficiency of the model. And we could use any number of folds. The folds could be up to n-1 observations. Don't worry, we will see cross-validation in detail in the later part of this module. For now, just use this formula to perform ridge regression. We will run this code and then we will store it in a variable cv_diab_ridge. Now let's see the explanation given here. The third argument type.measure is a loss function. Now here 5 options are available, and class is used for binomial and multinomial logistic regression. You can see the other classes by going to the help. After that, n-fold is the number of folds for performing cross-validation. We have already discussed this. Then family is binomial, which means logit function to be used. Now if you check the summary of cv.glmnet function, it returns many objects. But we are only concerned with minimum lambda for now, which gives us the minimum CV error. So for now, you can skip the rest of the details in the summary. So this is how model is created using the cross-validation approach. Now moving to the next part, it says let's make the prediction using test data and check the misclassification error. Now for this, first we have to extract the lambda corresponding to minimum error and then store it in a variable. So we will call this variable as lambda_ridge. We can extract this lambda from our ridge regression model that we have created in the previous step by using a $sign. So we have mentioned cv_diab_ridge $lambda.min. This will return the lambda for which validation error is minimum. Now we can make the prediction using the predict function. So the first argument for the predict function would be the model. So here we will use the cross-validated model, which is stored in cv_diab_ridge. And the second argument would be the test data, which is stored in x_test. Now third argument is the type, which is class. And the fourth argument is s, which is equal to minimum lambda. Now we will run this and we will get our prediction. So we will store our prediction results in a variable diab_pred_test2. Now once the prediction is made, we can create a confusion matrix and check the misclassification error. So we will again use table function. We will extract the first column from the predicted results. That will be our first argument. And the second argument would be the test data, which is stored in y_test. We will run this and we will store it in a variable cf_table2. Then we can print this confusion matrix. And like we did earlier, we will sum the diagonal elements and divide it by total. And then we will subtract it from 1. This will give us the misclassification error. Here it is 23.88. So if we go back and see the earlier misclassification error, It is somewhere around 27.3%. Hence, we can see that the error is reduced upon using the cross-validation approach. Now again, explanation is included. If you have any confusion, you can read through it. Now there is a small exercise given here. Once you have completed this assignment, you can try this exercise at home. I am skipping it for now. You can pause the screen and you can read through it if you want. Now I am moving to question 4. Now question 4 says perform Lasso regression and compare the results. So again we will set the seed here and we will use cv.glmnet function. Now all the arguments here will remain the same except alpha will be equal to 1. Remember, alpha is equal to 0 is for ridge regression and alpha is equal to 1 is for lasso regression. So we will run this code and we will store the results in cv_div_lasso. Now moving to the next part, it says make the prediction using test data and check the misclassification error. So again we will store the minimum lambda by subsetting it from the model. So we will write cv_div_lasso, then a $sign, then lambda.min. This will give us the lambda value for which the validation error is minimum. We will store it in a variable lambda_lasso. After that we will use the predict function. So the first argument would be the model and the second argument would be the test data, and then type would be class, and s will be the value of lambda for which validation error is minimum, which is stored in lambda_lasso. We will run this and we will store it in a variable diab_pred_test3. Now once we have calculated the prediction result, we can create a confusion matrix as we did earlier, and we will store it in the variable cf_table2. Then we'll print this confusion matrix, and after that we'll calculate the misclassification error. So here you can see the misclassification error is coming out to be 23.38. Now you can see that misclassification error rate from ridge regression was somewhere around 27%, and from cross-validation approach and lasso regression is somewhere around 23%, which is an improvement over ridge regression. Now we can use COA function and we can check coefficients of each of these models. So first we have printed the coefficient of lasso regression. Then we have printed the coefficients of ridge regression. Now in the end I have included the explanation. So let's read the explanation. First point says the error compared to ridge is almost similar. There is a marginal improvement only. However, we can vary parameters and may find better results. But the purpose of this assignment is to demonstrate the process. Hence, considering all other parameters same as ridge, we do not see any major improvement in the error. The second point says, in general, one major advantage of lasso over ridge regression is that the result coefficient estimates are sparse. However, in our case, even the coefficients are also similar to ridge. 4 coefficients are 0 in both the methods. So definitely there is a scope of improvement for this model. However, whichever approach we select, we are able to reduce the number of coefficients using both the approaches. So the main purpose of ridge regression or lasso regression was to reduce the number of variables that we are able to achieve from both the methods. Now if we compare misclassification error with logistic regression, we will get to know which method is performing better. So here is a small exercise for you to do at home. Build the model using logistic regression for this data and then compare the error. Alright, so that is all from this assignment for now. In this assignment, we have discussed ridge regression and lasso regression. And we have also seen cross-validation for implementing these two methods. After that, we compared the error of different approaches and also discussed how these techniques helped us in reducing the number of coefficients. So in total, we have learned 5 methods for variable selection. We will see one more method of dimension reduction, which is PCA, in the next module. And now in the next video, we will see another algorithm which is widely used for classification, that is naive Bayes algorithm. So I'll catch you up in the next video. Until next time, see you and take care.